So we've talked about how to find the methods of moments estimator by hand and the maximum likelihood estimator by hand, but that requires us to do really quite a bit of algebra. And even if we're comfortable doing that algebra, there's no guarantee that we're going to be able to find a nice closed form expression, basically a simple equation, that tells us what we need to do with the data to come up with the values of these estimators. And so in this day and age, it's actually much easier to solve for the methods of moments estimator, or the MLE, just on a case-by-case basis, doing numerical optimization of the likelihood or numerical matching of moments with fitdist or other sorts of routines that software allow us to do. So let's talk about the savior of how we can do some estimation for these unknown parameters just numerically using the fitdist function in R. Now, one nice thing is that most of the notorious distributions actually already have simple rules that tell us what we need to do to come up with the MLE estimate, or the methods of moments estimate. For instance, if we're trying to estimate P, the probability of some event occurring, technically that's estimating a parameter of a Bernoulli distribution, success versus failures, ones versus zeros. We know that the best estimate here, the MLE or the methods of moments estimator, says take X bar. Take the average of the ones and the zeros. Success is 1, failure is 0. That's the proportion of trials where your event of interest occurred, and that's your simple rule for how to come up with the estimate of P. For the Poisson distribution, well, there's a simple rule as well. If you want to estimate lambda for a Poisson, just take the sample average. The methods of moments, maximum likelihood estimator agrees. For the geometric distribution, we want to estimate P, basically the probability of success here. We're conducting a bunch of trials. They're failing, they're failing, they're failing. We're waiting for that first success to occur. The geometric is counting up the number of trials, number of failures before that very first success. So if we ask everyone in the class to go and perform this experiment, everyone measures their own value of X, the number of failures before that first success. Well, the MLE says to take that average value of X across the whole class, and your p hat is just 1 over 1 plus the sample average. So a lot of these notorious distributions already have these simple rules, and if you've committed them into memory, then that saves you a little bit of time, but there's really no need to have all of this at your disposal, at your memory, because fitdist will actually take care of you and come up with what the answer is for the MLE or the methods of moments estimator for any case you can really come up and think of. So the other slides tell you what these simple rules are for how to estimate, say, mu and sigma of a normal distribution, mu and sigma of a log normal distribution, etc. But some of these distributions we just have to use fitdist anyway. So beta distribution, Weibull distribution, there are no simple rules. We have to solve it on a case-by-case basis numerically. So how are we going to use fitdist? Well, if we're dealing with the notorious distribution, this is something we've already done before actually. So we'll run fitdist. X is going to be the vector containing our data values, and we'll just put in the name of the distribution as R knows it in quotes. So unif, norm, Poisson, exp, etc. We can get a summary of the fit if we left arrow it in to an object called fit in all caps, and we can even see how good that probability distribution fits the data with plotting the fit. So to get the MLE estimate, that's what's going to happen by default by running fitdist. If we really want the methods of moments estimator, well, we can say method equals MME. But as we've discussed, there's really no reason to do the methods of moments estimator when the maximum likelihood estimator can be found with fitdist. For all intents and purposes, the MLE is the best estimator out there in the very general case here. So how does this work? Well, let's just go through a few examples. Let's fit a distribution to a beta. So let's go ahead and just generate some data values. I'm going to do observations, left arrow, and let's use the R function with beta. So this will generate random numbers from a beta distribution. Let's generate 419 of them with the parameters shape 1 equals to 1.5. and shape 2 equals to 0.8. So in this case, I actually know the answer. The two parameters are 1.5 and 0.8. Let's actually just take a look at what the data looks like here. So if we go and check out a plot, well, we find that they seem to be steadily increasing up towards larger values. So if I just had this data set and I wanted to model this with a beta distribution, well, what's going to be my MLE estimates for these two parameters? Well, easy enough. We're going to run fitdist. The first argument is going to be the vector containing our data values. I've named that observations. And since R knows about the beta distribution, by just the abbreviation beta, we put that in quotes as the second argument and we run it. And of course, we got to make sure that library is loaded up. But once the fitdist or plus library is loaded, we automatically get this. We get a summary of the fit where we can see, well, what are the MLE estimates? So it looks like that first parameter, the MLE is about 1.54, pretty darn close to what we happen to know the truth is. The MLE estimate for the second parameter, 0.84, pretty darn close, so good job. We can check the goodness of fit, basically, if we make a plot of that distribution that gives us more than what we need to see, or we can just look at the QQ plot with QQ comp. Brilliant. Looks about as good as we're ever going to see. In this case, since the data really is coming from a beta distribution, it's no surprise we have such a good fit. But if we're dealing with one of these notorious distributions, that's really just what we're going to do. We're going to use fitdist and just provide the name of the distribution as R knows it. So, for example, if I had a Poisson distribution that I wanted to fit to the data, let's just make some data here. And in this case, I'm just going to kind of put in a whole bunch of random numbers here just by hand, just to illustrate. I'm not going to generate the data values with our Poisson individually because, in general, I'm just presented with some data. I don't know where that data really came from. So I need to put in one more number there. And let's just take a look at the data values that we have. So that's my histogram. I want to fit it to a Poisson distribution. What's going to be the MLE estimate for lambda, the parameter of the Poisson distribution? Well, put in as our first argument whatever my data vector is. Second argument, in quotes, the name of the distribution as R knows it. So let's fit it to the Poisson distribution. And it looks like the MLE estimate is to have the lambda parameter be 2.79 or so. So is that a good fit? Well, remember, since we're dealing with the discrete distribution, we don't really want to do QQ plots for this. That's really more designed towards continuous variables. So instead, I'm going to plot that fit instead. And we'll look to see if we have a good concordance between the empirical distribution function, the fraction of data values that are less than or equal to a certain value, and what we expect based on what the PMF that's been proposed. So we look at the dots, we check to see do they fall close to the outer corners of these stairs. Well, the answer is no, this isn't really a great fit. And in fact, comparing the empirical and actual actual frequencies of each of the data values with what we expected from a Poisson, we expect is in red, what we observed is in black, we don't see that great of a match. So in this case, the Poisson's not that great of a fit here. But if you're dealing with one of these notorious distributions, easy enough. You have your data vector, that's your first argument, and you just say, well, what's the abbreviation for your notorious distribution? Is it beta, Poisson, unif, norm, L-norm, Weibel, exp, gamma, etc.? Now, what's fantastic is that you can even define your own custom distributions and have fitdist do the same sort of thing. Now, it's going to depend a little bit, the procedure at least, on what you want out of the fit. If you just want the MLE estimates, it's very easy. If you want to make these plots, that's going to require you to do a little bit more work. And so let's talk about the easy case where we just want to get the MLE out of it. So here I've named a distribution after myself, the Petri distribution. Rather egocentric here, but let's go with it. And the formula for the PDF of a Petri distribution is this right here. X over this Greek letter phi squared, e to the minus x squared over 2 times phi squared here. So what if I wanted to fit a set of data to this probability distribution? Well, how would I do that? So let's start out with some observations. And I'm going to generate some observations just at random, but from a Weibel distribution with these parameters right here, 3 and 8. So the truth is my data isn't coming from a Petri distribution, it's coming from a Weibel distribution. But if I'm going to propose a Petri distribution and I want that MLE for this unknown phi parameter, what should I take based on the data? All right, so here's going to be the procedure. All we need to do is define a PMF or PDF for the distribution we want to fit and give it a name. So I'm going to use the name custom, and R is going to require us to always define a function called dCustom. So just like how dPois gives you the values of the PMF from a Poisson distribution, dBeta gives you the values of the PDF from a beta distribution, dCustom is going to give me a chance to specify what is the formula for my PDF or PMF that I want to fit. So I'm going to left arrow that to the keyword function, make sure that's spelled correctly. My first argument is always going to be x, and my additional arguments are going to be whatever parameter or parameters I'm going to be trying to estimate from my distribution. In this case, I just have one. I'm going to type that out as PHI, phi, and then in curly brackets, all I need to do is type out the formula. So transcribe this into R speak. So x over phi squared times e raised to the minus x squared divided by 2 times phi squared. And once I have this, fitdist is able to take care of us. So if I wanted to figure out, say, the mathematical solution for the MLE, what the shortcut is, what I need to do with the data, what statistic I have to calculate in order to best guess phi, that would require about 15 minutes of algebra using Wolfram Alpha. Look how easy this is going to be for fitdist. I say fitdist, well, my vector containing my data is observations. And since I've named my function dCustom, that D is saying, hey, this is a PDF or PMF, this is what I'll have to put in quotes, whatever follows the D here. So I'll just put custom here. And when I do this, I need to give it a little nudge, since it's a custom distribution, and say, okay, here's where you should start your search for what the MLE value is. So all numerical optimization algorithms need some sort of starting guess. Now, it doesn't have to be a good starting guess. It doesn't have to be close to what the solution is. It just needs something to get started here. So I have no idea what the MLE for phi is. So let's pass the additional argument start equals list, and then phi equals 2. So whenever we're dealing with a custom distribution, we'll have this additional argument start equals list, and then in this list, we'll just put starting guesses for the parameter for parameters here. So let's just start it out. Let's guess it phi equals to 2. It's always going to give a warning message just saying, hey, this pCustom function must be defined, and we don't actually need that. To get the MLE, we don't need this pCustom function. That's only going to come into play when we want to make these fancy diagnostic plots. So don't care for this case. I just want to know what's the MLE estimate. So once it's done it, I can get a summary of what this phi is, and it comes out with an estimate of minus 5.3. Now, I know that in this case, phi should be a positive number. So I must have done some sort of mistake with my transcription, and so let's go and revisit this. So x over phi squared looks good, times e to the minus x squared divided by the quantity 2 times phi squared. Okay, well, it doesn't look like I've made any sort of error, so let's try it out with a different starting value. And there we go. So notice by changing the starting value, all of a sudden I actually get the same number, just with the sign flipped. And that's really a consequence of how I've written the definition of this PDF. Notice that I only see a phi squared in this definition. So if I were to square minus 5.3, I'm going to get the same value as 5.3 here. So same sort of difference. I just had to use a little bit of logic and a little bit of insider knowledge, knowing that phi should have been a positive number. I want it to be a positive number. But we can see that, the starting guess really isn't going to change our conclusion here. Sometimes we get the positive estimate, sometimes we get the negative estimate out there. In general, this won't be an issue. It just needed a starting guess, and as long as we were there, we got basically what the answer is. All right, well, how about a more complex solution or example here? Let's do an example. Scroll ahead a few pages into the notes here. Or actually, let's do one more simple example. Let's do the logarithmic distribution before moving on. Simple example because there's only one parameter estimate. So let's try this logarithmic. Let's make some data. So observations. And this is nice right here. Let's just go and paste that if it's going to let us paste it. No, not going to let us paste it. Well, let's open up the corresponding R file and get this for us. So you can always download these .r files onto Canvas. And in this case, we're going to be looking at dcustom for the logarithmic here. So here's our logarithmic example. I'm just going to borrow this. Here's our observations. We have some data to play around with. So how can I best estimate what p is? So this logarithmic distribution has values of 1, 2, 3, 4, etc. for x. It's actually been used to model brand name abundances. So when you go and scour someone's household and you count up, say, the number of brands of toothpaste, say that's in their storage closet that they're currently using, the logarithmic distribution might give you some sort of insight as to the values you might see in their respective probabilities. So 1 brand, 2 brands, 3 brands, etc. What might we see? So if we had this as our data, well, what would we best guess the parameter p to be if we're going to use a logarithmic distribution? Well, fitdist will help us out. I'm going to always call these custom distributions just dcustom here. And in this case, I'm just going to type out left arrow function x comma p. First argument's always x. Second argument is going to be just whatever the placeholder is for that unknown parameter you're estimating, p in this case. If there's more than one parameter, we just add in additional arguments. So transcribe now, inside the curly brackets, our formula. So minus 1 over the log of 1 minus p times p raised to the x over x. All right, easy enough. Fitdist, help us out here. What is the MLE estimate for p here based on the data? So first argument of fitdist is the name of the data vector having our observations. The second argument is going to be the name that I've given my custom PMF here. So because D prefaces custom, custom's going to be in quotes. And then I have to give it a starting guess. So in this case, P is going to be between 0 and 1. Let's just take it right in the middle. And we'll run it. Same warning message. We don't care about that. That's only necessary if we want to make plots. And we'll look at a summary. Looks like the MLE is about 0.77. Now, is that sensitive to my starting guess? No. If I change this up, if I change it down, it's not really changing whatsoever. It's always a good idea to try out a few values just in case the likelihood was really tricky to actually maximize here. Most of the likelihoods we deal with are very straightforward. There's only a single maximum. There's no other local maximums that might fool the algorithm. So we converge to the MLE estimate, no problem. All right, harder example. Let's take a look at what's known as the logistic distribution. Kind of looks like a normal distribution, allows negative, positive numbers. It's symmetric, it's unimodal. Bit easier to work with mathematically, but it has two parameters. This M parameter, which describes where the peak is actually, and this S parameter that describes how thick this curve is. So kind of like the standard deviation, the sigma parameter of a normal. And let's try it out. So let's get some data here. And let's just make observations from a normal distribution. Let's make 409 observations with a mean of, let's say, 41 and an SD of 100. So let's just look at what our data looks like in this case. So I just use that R norms just so we have something to work with. So symmetric, we got negative, positive numbers. What if we wanted to fit this logistic distribution to it? Well, two unknown parameters here, M and S here, but easy peasy. All I need to do is define my dcustom distribution. And because I have two unknown parameters, well, I'm going to add two arguments, M and S. First argument's always going to be x. And I just need to transcribe what the formula is. So 1 over s times e raised to the x minus m over s power divided by 1 plus e raised to the x minus m power over s. And this denominator here was being squared. So that's defined. Let's run fitdist. So observations, whatever the name of my data vector that's containing my data, make sure that is the first argument. Second argument will be custom in quotes because that's the name we chose that followed the D. And we have to give it some starting guesses. So since there's 2 unknown parameters, 2 starting guesses. So let's just choose m of, since we know this is kind of where the peak is, if I just look to see, well, where's the peak? You know, it's maybe around 25 or so, so 25. And s, well, it's kind of like a standard deviation, so how thick is this curve? How far is it from the peak to kind of the inflection point where it goes from sloping down to sloping out? Maybe it's about 100 or so. Let's go for it. Same old warning message, don't care. Let's get a summary. And this is estimating m to be 321 and s to be 275.1. Is that sensitive to my starting guesses? Well, let's just switch this up. Same values here. 320, 275. Even if I'm really, really far off, R is smart enough to know how to find that maximum. So we always get there. So how good a fit is it? Well, unfortunately, since I haven't defined the P and the Q functions, I can't do QQ comp. I can't plot the fit. Notice when I try to do that, it says, no, I can't do that. I need that P custom function. That's why that warning was there. But what I can do is superimpose this curve on the histogram. So let's make that histogram again, but let's add freq equals false so that we can overplot the PDF. So how can we add that PDF? Well, let's add a curve of D custom with these 2 unknown parameters. The ones we guessed, let's just copy and paste this and this. We'll add equal truth, and we'll make this red. Well, that's pretty disappointing here. Unfortunately, it doesn't look like it did a great job actually fitting the data. But that's life. Let's make sure that we actually calculated or transcribed this equation appropriately. Looks like we did. Let's try the example in the notes. That's kind of fun. So in this case, m is 2, s is equal to 10 here. And let's go ahead and make, oh, that was just a plot. So let's make some new data, peaking at 30, standard deviation of 5. That's what it looks like. D custom, fit it, make a summary of it, and then we can add a curve. Freq equals false, and then curve it. D custom x 29.6, 2.85, and that looks a lot better. So going back actually to the example we were just working on, let's make a histogram of this. And we'll get the summary of the fit. And this is why, let's make it again. There's my histogram. And let's go ahead and put these in here. Boom. Now we got a good fit. So it's too bad I didn't set that random number seed because, you know, Could have checked to see if anything went wrong there, but if I run this again, I'm going to actually go and say fit estimate 1 and fit estimate 2 just to automatically actually make this. So that one's pretty tragic. Yeah, there must be some issue that I have with the transcription here. So let's take a look. 1 over s times e to the x minus m over s divided by 1 plus e the x minus m over 2. There's an s there. So embarrassing. See, even after 20 years of programming in R, I make these silly mistakes. And look at this. Every time, bam, 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 bam. Great fit after great fit after great fit. Fitdist to the rescue. So there we go. Do we need to know how to solve mathematically for these MLEs, these methods of moments estimators? Well, not really in this day and age, especially if you are a business analytics practitioner. You know, this isn't something you're going to be doing on a daily basis. If you want to get the MLE for something, then hey, fitdist to the rescue. So why does this whole mathematical procedure exist? Why did I make you do this on the homework? Well, you know, back in the day, in my time, we didn't have computers. We didn't have fitdist. We didn't have R. We didn't have numerical optimization. So this was literally the only way that you had to figure out what the best guesses were for these unknown parameters based on the data. So before computers, you really didn't have a choice but to go through this mathematically. And here's the problem. Once something has happened for a long enough time, it's kind of slow to change. So people in the field, especially in statistics, still kind of expect you to be able to do this procedure by hand, even though we kind of know how to do it numerically much more quickly than what we could do it by hand, and for a much wider variety of problems. Not every single PDF you could actually come up with the MLE for with a nice closed form expression. So, does anyone care if you solve for the MLE by hand anymore? Well, unfortunately, the answer is yes, but mostly if you're a statistics major. And that's just because it's been done for so long, people kind of expect you to do it. Now, we know better. This really isn't a skill that we have to have because we can come up with the MLEs on a case-by-case basis, no problem. But, you know, part of the playing the game is making sure we satisfy other people's expectations. But, hey, we'll be able to do it on the case-by-case basis. But I think the only advantage, really, of being able to do this procedure by hand, coming up with what exactly do you measure from the data, that nice simple rule for what you have to calculate, I think the big advantage is that it's kind of neat. You know, it adds a little bit of insight into the problem. You know, if we're dealing with a Poisson distribution, it's kind of nice to know that, hey, you want to know what lambda is? Just estimate x bar. If we're dealing with a random sample from a geometric distribution, hey, you want to know what p is? Oh, well, just take 1 over 1 plus x bar. It's kind of nice to have that simple rule, but, you know, is all that math really worth something that's just kind of nice? Well, I'll leave that up to you. I love it. I will do it every single day, but your mileage might vary. So fitdist is fantastic, and I encourage you to use it from here on out here. So if you just use fitdist for every single day in the rest of your life, what you're really giving up is just that understanding of where that MLE comes from, what that simple rule is, like taking the reciprocal of 1 plus x bar. But you open up the world to a much greater variety of probability distributions where you can fit, and it's just a lot more quickly. You know, algebra, you can make mistakes. Transcribing equations, you can still make mistakes like I just gloriously showed. But hey, fitdist, fantastic tool for you to use. So the rest of the notes here give you this streamlined procedure for estimating 1 parameter, estimating 2 parameters. Have these examples once again. The only caveat I want to leave you with is that fitdist can still fail if you run into one of those special cases. Now, we've talked about that whenever we run into a case where the value of our unknown parameter is tied in to the possible values of x that we might observe, our standard method of writing out the likelihood, taking the derivative, shipping it out to Wolfram Alpha or whatever, is going to fail us. Numerical optimization, going to fail us as well, because 99.9% of the time, the optimal value of that unknown parameter is going to be on the boundary of either the largest or the smallest value of the x's. And numerical optimization, not quite smart enough to figure that out without a lot of extra built-in steps. Well, from alpha, not smart enough to actually figure that out unless we explicitly say, hey, you have to search within a range. So just be careful. Whenever you have that unknown parameter tied into the possible values of x, you're still going to have to write out that likelihood. You're going to have to use logic to figure out where the peak is. Fitdist can still fail you here. But otherwise, hey, you're good to go. You now know how to estimate MLEs of any probability model someone can throw at you, little asterisks, except for the ones where x is related to the value of the unknown parameter.